The year is 2025. In a laboratory at Northwestern University, a pulse of light flickers through a fiber optic cable. To the casual observer, or even a standard network diagnostic tool, nothing unusual has happened. The cable is busy. It is humming with the chaotic traffic of the modern internet. Netflix streams, high-frequency stock trades, and endless social media scrolls are racing through the glass strands at the speed of light. But hidden within that cacophony of classical data, a ghost has just passed through. A single photon, carrying a delicate quantum state, has been teleported across 30 kilometers of active infrastructure without being destroyed by the noise of the mundane world. This experiment, achieved in late 2024 and solidified by peer-reviewed triumphs in 2025, marks the end of science fiction and the beginning of engineering reality. We are no longer just theorizing about a quantum internet, we are laying the cables for it. The quantum internet is not merely a faster version of the web we use today. It is a fundamentally different beast, operating on the counterintuitive laws of quantum mechanics. It does not send emails. It teleports states of matter. It does not just encrypt data. It makes eavesdropping a physical impossibility. And most importantly, it promises to link the isolated islands of today's quantum computers into a global superbrain capable of solving problems that would take a conventional supercomputer the age of the universe to crack. Today, we are going to break down the physics, the engineering, and the implications of the most ambitious project of the 21st century: the effort to teleport data across the world. To understand the quantum internet, you must first unlearn the rules of the classical internet. The internet we know today is binary. It is built on bits. These are electrical or optical pulses that represent either a 0 or a 1. When you send an email from New York to Tokyo, you are essentially sending a stream of these bits. They are copied, amplified, and routed through dozens of servers. If a packet is lost, it is simply resent. If a hacker intercepts it, they can copy the stream without you ever knowing. The quantum internet abandons the bit for the qubit. A quantum bit, or qubit, can exist in a state of 0, 1, or a complex combination of both simultaneously. This is a phenomenon known as superposition. Imagine a coin spinning on a table. Is it heads or tails? While it spins, it is effectively both. Classical computing is like stopping the coin and looking at the result. Quantum computing is the ability to perform calculations on the spinning coin itself. But the true backbone of the quantum internet is not just the qubit itself, but a phenomenon called entanglement. This is what Albert Einstein famously dismissed as spooky action at a distance. Yet, it is the fundamental mechanism upon which this new network relies. When two particles, like photons, become entangled, they lose their individual identities and share a single quantum state. No matter how far apart you separate them, whether one is in a lab in Chicago and the other is on a satellite orbiting Mars, measuring the state of one instantly determines the state of the other. This connection is instantaneous. It ignores distance. In the context of the quantum internet, entanglement is the cable. If Alice in New York and Bob in London share a pair of entangled photons, they possess a private, unbreakable link that bypasses the physical space between them. However, this brings us to the central challenge of building this network. In the classical world, information is cheap because it is copyable. In the quantum world, the no-cloning theorem dictates that you cannot create an identical copy of an unknown quantum state. If you try to copy a qubit, you disturb it, destroying the information it carries. This property is a double-edged sword. It makes the quantum internet theoretically unhackable because a hacker cannot copy the data, but it also makes it incredibly difficult to build. You cannot use standard signal amplifiers to boost a dying signal, because amplifying means copying. This forces engineers to invent entirely new ways to move data, leading us to the concept of quantum teleportation. When we hear teleportation, We usually picture science fiction where a person dissolves in one spot and reappears in another. Quantum teleportation is less about moving matter and more about moving information, specifically the precise quantum state of a particle. It is best understood as the ultimate fax machine, but with a catch: the original is always destroyed in the process. Let's break down the protocol of how data is teleported across a quantum network using the standard characters of cryptography. Alice and Bob. Alice is the sender. She wants to send a specific quantum state, let's call it qubit X, to Bob, the receiver. She cannot simply measure qubit X and tell Bob the result, because measuring it would destroy its superposition. This is where the resource of entanglement comes in. Alice and Bob already share a pair of entangled particles, particle A and particle B. Alice holds A and Bob holds B. To initiate the transfer, Alice takes her qubit X and interacts it with her half of the entangled pair, particle A. She performs a specific operation, called a Bell state measurement. This measurement forces qubit X and particle A into a specific combined state. Crucially, this interaction destroys the original state of qubit X. The information seems lost locally. However, at the exact moment Alice performs her measurement, Bob's particle, particle B, instantly transforms. It adopts a state that is mathematically related to the original qubit X. However, Bob doesn't know how it is related yet. To complete the teleportation, Alice looks at the result of her measurement, which will be two classical bits of data, for example, 0, 1. She sends this result to Bob via a normal internet connection, a fiber optic cable, or a phone line. Bob receives the two bits. Based on this information, he performs a simple rotation on particle B. Upon doing so, particle B becomes an exact replica of the original qubit X. The information has been teleported. It did not travel through the space between them. It utilized the pre-existing entanglement bridge. Note that the transfer wasn't complete until the classical data arrived, which is limited by the speed of light. This preserves causality and prevents information from actually traveling faster than light, even though the quantum connection is instantaneous. Now, let's move from the physics to the engineering. Building a network that can sustain these fragile entangled states across continents is a monumental task. The infrastructure of the quantum internet is currently rising on three pillars: flying qubits, quantum repeaters, and transducers. To move quantum data, we use photons, which are particles of light. Photons are excellent flying qubits because they don't interact much with the environment. They can travel through the vacuum of space or through the glass of fiber optic cables. However, photons have a weakness: attenuation. As they travel through fiber, some get absorbed or scattered. In classical networks, we put amplifiers every 50 kilometers to boost the signal. But because of the no-cloning theorem, we cannot amplify a quantum photon. If a photon carrying a qubit is lost after 100 kilometers, the game is over. To solve this distance limit, scientists are developing the quantum repeater. This is the most critical hardware component of the future internet. A quantum repeater works by a process called entanglement swapping. Imagine Alice is 100 kilometers away from Charlie, and Charlie is 100 kilometers away from Bob. Direct transmission from Alice to Bob is impossible due to signal loss. Instead, Alice establishes entanglement with the repeater, Charlie. Bob also establishes entanglement with the repeater. The repeater then performs a Bell state measurement on the two photons it holds, one linked to Alice and one to Bob. Magically, the entanglement is swapped. Alice and Bob are now entangled with each other, even though their photons never directly interacted. For this to work, the repeater needs quantum memory. It must be able to catch a photon from Alice and hold it in a quantum state, perhaps by transferring its state to an atom or an ion, while it waits for the photon from Bob to arrive. In 2025, research from the University of Chicago extended the coherence time or memory life of erbium atoms to over 10 milliseconds. While this sounds short, In the world of light-speed data, it is an eternity, theoretically allowing connections up to 2,000 kilometers. This brings us to the recent breakthrough at Northwestern University regarding coexistence. Until recently, it was assumed that the quantum internet would need its own dedicated fiber cables. The noise from classical internet traffic is billions of times brighter than the single photons used in quantum communications. It is like trying to see a firefly while staring directly into the sun. However, researchers found a safe zone, a specific wavelength within the standard fiber optic spectrum that is less prone to scattering noise. By using specialized filters and synchronization, they successfully teleported quantum states over 30 kilometers of cable while it was fully loaded with active internet traffic. This is an economic game changer. It means we do not need to dig up the entire world to lay new quantum cables. We can ride the dark wavelengths of the existing infrastructure. So why go through all this trouble? Why spend billions to teleport a few qubits? The answer lies in 3 revolutionary capabilities: unhackable security, distributed computing, and the quantum telescope. The immediate application, which is already in use by banks and governments, is quantum key distribution, or QKD. In current encryption, like RSA, we rely on difficult math problems, such as factoring large primes, to keep secrets. If a hacker has enough computing power, or a quantum computer, they can crack the code. QKD uses the laws of physics. Alice and Bob use the quantum internet to generate a shared encryption key. If an eavesdropper tries to intercept the photons creating this key, she inevitably disturbs their quantum state due to the observer effect. Alice and Bob will instantly notice an error rate spike in their data. They know they are being watched and can discard the key. Metro-scale QKD networks already exist in Beijing, Vienna, and parts of the US. The quantum internet will globalize this, creating a planetary shield for data. The second killer application is distributed quantum computing. This is the long-term vision. Current quantum computers are limited by the number of qubits they can fit on a single chip. It is incredibly hard to keep 1,000 qubits stable in one refrigeration unit. The quantum internet allows us to take 10 small 100-qubit computers and link them together via entanglement. To the algorithms, they would look like a single, massive 1,000-qubit machine. A modular, distributed quantum supercomputer could simulate complex molecules for drug discovery, model climate change with unprecedented accuracy, or optimize global logistics in real time. The third application is blind quantum computing. Imagine you have a powerful quantum algorithm you want to run, but you do not own a quantum computer. You want to use a cloud quantum computer, but you do not want the provider to know what you are calculating. The quantum internet enables you to send qubits to the cloud server in a way that the server performs the calculations without ever knowing what the inputs or outputs are. The server is blind to the data it is processing. Only you, holding the entangled keys, can interpret the result. Finally, we must look at the global race and the road ahead. The construction of the quantum internet is Space Race 2.0. China currently holds the record for the longest quantum link. The Mikia satellite, launched in 2016, successfully distributed entanglement between ground stations over 1,200 kilometers apart. China is aggressively building a ground-based backbone connecting Beijing to Shanghai. The United States is moving toward a hub model. The Department of Energy has published a blueprint connecting its national labs, such as Fermilab and Argonne, into a prototype quantum internet. The recent success in Chicago regarding teleportation across active cables gives the US a significant edge in infrastructure scalability. Europe, through the Quantum Internet Alliance led largely by TU Delft in the Netherlands, is focusing on the repeater technology. They have defined a clear roadmap, moving from simple trusted nodes to fully entangled networks. We are currently transitioning from Stage 1, which involves trusted nodes, to Stage 2, which is true entanglement distribution. From 2025 to 2027, we expect to see the first memory-based quantum repeaters, tested outside of labs. By 2030, we anticipate the integration of satellite and ground networks. Satellites will handle intercontinental links where fiber loss is too high, while fiber handles the last mile within cities. The quantum internet is not replacing the classical internet. It is evolving alongside it. Just as the electric grid and the internet converged to create the modern smart world, the classical and quantum webs will merge. We are standing on the precipice of a new era of connectivity. An era where distance is conquered not by speed, but by the eerie, instantaneous connection of entanglement. An era where information is physically secure by the laws of nature. The teleportation of data is no longer magic, it is infrastructure. And the cables are already humming.